likelihood ratio test. In this module, we try to develop tests that can be used to test the general type of hypothesis known as the likelihood ratio test. Actually, that test is based on the likelihood ratios of the null and alternative hypothesis. How we proceed for this one? Let x, which represent in term of vector, be a random variable with the probability density function or the probability mass function, that is f of x theta, where theta belongs to parameter space, and we want to test, that is h naught, theta belong to the capital gamma naught, basically that is the subset of the parameter space, versus h1, that is the alternative hypothesis, theta belong to the gamma, capital gamma 1, which is another subset of the parameter space, and where capital gamma naught union of gamma 1, that is actually the equal to the parameter space. So how we proceed for this one? Let us write down their likelihood functions of the two, one based on the null hypothesis and other based on the alternative hypothesis. So you can see that the likelihood function can be written as theta belong to the theta naught, that is actually based on the null hypothesis. जब theta capital gamma को belong कर रहा है, capital gamma naught को belong कर रहा है, तो which means that is actually the likelihood which represent the null hypothesis. So that can be written as the supremum of the theta belong to the capital gamma naught, L of theta x, and that is actually denoted by L hat gamma naught. And the other, which is the alternative hypothesis on the same line, you can see that just only one minor change, that is in term of capital gamma. Here actually capital gamma represent gamma 1, and the likelihood function which is based on the alternative hypothesis can be written as the supremum of the theta which belong to the gamma 1, that is L of theta x, and that is denoted by L capital gamma 1 hat. Then we consider the ratio. You know that actually the likelihood ratio, the test is basically based on the likelihood, so that is actually R of x, and that is actually the ratio of the likelihood which is based on the alternative hypothesis and the likelihood which is based on the null hypothesis. So how we define the critical region? Then R of x greater than k is the possible rejection region. So how we define that this is the possible rejection region? So very obviously the criteria is very clear. If h1 has the higher value, then L gamma 1 hat is more likely occur, and if h naught is the more likely occur, then definitely the L gamma naught actually has the higher value. So therefore the rejection region for the large value of this ratio, and the acceptance region for the small value of this ratio. This ratio actually requires two type of maximization. So when we are doing two types of maximization, there is a bright chance that we face some sort of problems in finding some maximization. So just for example, in term of alternative hypothesis, if our alternative hypothesis is one-sided, then we face some sort of problems in determining the maximum likelihood function. So to avoid this problem, another equivalent procedure can be adopted by the considering the full parameter space. So instead of considering the alternative hypothesis, we consider the full parameter space. On the same line, actually theta belong to the capital gamma, that is the supremum of this one, because we are interested to find the likelihood function. So L of theta x, basically that is denoted by L hat capital gamma, and this is actually based on the full likelihood function. So we define the ratio now, that is lambda x, and that is actually L hat capital gamma naught, which is based on the null hypothesis, divided by the L hat capital gamma, actually that is the based on the full parameter space. So we have two ratios, two functions. One is based on the full likelihood function and one is based on the null hypothesis. The likelihood ratio is to reject h naught if lambda x is less than or equal to c. Very obvious, the denominator is a larger value. So the criteria for the rejection region is that lambda x is less than c. Since the denominator is the maximization of the full parameter space, as just I explained that, therefore naturally we find this range of lambda x, that is 0 less than or equal to lambda x less than or equal to 1. And the constant c is determined from the size condition. So what are the size conditions? Size condition can be written as the probability under the null hypothesis that lambda x less than c is equal to alpha. If the distribution of the lambda x is continuous, then the size alpha is attainable. In almost all the cases, it is observed that if the distribution is continuous, we may able to find the distribution. We may be able to find the size alpha, test of size alpha. In case of lambda x is discrete, it may not be possible to derive the likelihood ratio test exactly. So this happened because this type of test is actually non-randomized test. So we have some problem in term of some sort of discretization when lambda x is follows some sort of discrete distribution. So we have some problem to find the likelihood ratio test.